Hi guys, my name is Abdullah. I'm a student in avionics engineering in Emirates Aviation University. Today I will be talking about Kepler's laws of motion. Specifically, actually, in this particular video, I'll be talking about Kepler's first law of planetary motion. So let's write this down. Kepler's first law of planetary motion. Okay, now in this Kepler's first law of planetary motion, this is a very amazing application of vectors, application of vector calculus, cross and dot product of vectors, components of vectors, a very nice application of all the different aspects of vectors and vector functions. In Kepler's law of planetary motion, to derive the Kepler's first law, I'll tell the first law in a bit. To derive the first law of Kepler's planetary motion, we will have to use Newton's second law of motion and obviously our knowledge of vector mathematics. Okay. However, there are some assumptions that we need to make. So, first of all, before writing those assumptions, what does the Kepler's first law says? So, the Kepler's first law says that all planets revolves in an elliptical path around the sun, or I would say with the sun, in the focus. Okay, that means that Kepler's first law of planetary motion says that all planets, or a planet you can say, revolves around the sun in an elliptical path with the sun in the focus, which means with the sun in the center of attention, you would say, or you would say that the sun is the basis of the path. Okay, so this is the first law. I hope you guys noted it down. So let me just go ahead and write down an assumption for Kepler's law. So the assumption states that whenever we are deriving Kepler's law, we think that there is no effect from other celestial bodies. There is no effect from other celestial bodies. That means that we will only consider one sun and one planet. That planet can be a moon, it can be a satellite, a man-made satellite. So the application does not only depend on the motion of the planet. This planetary, I actually mean moons, satellites, planets, anything revolving around the star. A star can be the sun, the star can be a planet itself with the moon revolving around it. It can be many things actually. Okay, now let's start with the derivation. Okay, so to start with the derivation, let's say that we have to use Newton's second law of motion. What does Newton's second law of motion say in vector form? That the force vector F is equal to the m mass into the acceleration vector. Now listen, you have to be very careful about this mass. This mass is the mass of the planet. So this is the force felt by the planet, which is revolving around the sun. So m, I'll write down here, m is equal to mass of planet. Okay. Now we have Newton's gravitational law. So what does Newton's gravitational law says? Newton's gravitational law says that F is equal to negative G m capital M small m over, right here, you have it right here, the position vector square into the position vector over the magnitude of the position vector. Okay? So let me just write down here. We already defined what is M. We can define what is G. G is the universal gravitational constant. Universal gravitational constant. Okay. What is capital M? Capital M is the mass of the sun. Mass of the sun. Or, if you say you have a planet and a satellite is a much smaller mass, have a much smaller mass than a planet, so capital M would be the mass of the planet and small m would be the mass of the satellite. Okay, keeping these things in mind, we can go ahead and we can write that this particular path, this particular thing is actually called the unit vector. So the unit vector can be written as r over r prime, okay? R over the magnitude of r, which can be written as r over the magnitude of r. So I'll just represent the magnitude of r with a simple r with no cap on it. That means that this is not a vector, just a constant. Okay? So using these two formulas, since these are two force equations, we can equate them. I will replace this one, r magnitude of r, the vector r square, with this, just a simple r square, and I will replace this with the unit vector u. So let's go ahead and do that. So we have the two forces are equal, so u is equal to, okay, from here you can see m is a common factor. You can cancel the common factor out. You'll be left with this vector. Okay, so when you're left with this vector, we now have an equation for A. So let's write it down here. A is equal to So now let's go ahead. Now our job would be to prove that the rotation of the planet, that means the path of the planet, the path the planet takes is actually in one plane. So we'll go ahead and we will do that. We have a formula for A, acceleration, right now. From this formula, we can actually get two different things. So let me just mention those two different points which we can actually derive. The first point from this formula. So the first point from this particular formula we can get is the acceleration vector of a planet is parallel to its position vector. Now, how did I come to this conclusion? If you notice this formula, the acceleration vector is equal to negative of a constant into the unit vector u. So what is a unit vector? the unit vector is actually the unit position vector. Okay, so if the acceleration vector is parallel to the unit vector, it will obviously be parallel to the actual position vector. But there is another conclusion that we actually can make from this. The second conclusion that I would make is the acceleration vector and the unit vector and the position vector are actually in completely opposite directions. The acceleration vector is completely opposite in direction to the position vector. Again, I could have said the unit vector, but it's the same thing. The unit vector is actually the position vector, the direction of the position vector. Okay, so the two things we notice. First of all, the acceleration of a planet which is revolving around the sun is actually parallel to the position vector of the planet in its orbit. The second point, the acceleration vector is completely opposite to the position vector because you see of the negative sign. Now the third thing that we have to, right, I hope you guys wrote these 2 points. The third conclusion that we can make, the third conclusion from this formula is, and it's a very interesting conclusion to be honest. The third conclusion that we make can we make from this formula is that the acceleration of a planet does not depend on its mass. Does not depend on its mass. It's very interesting. And I'll tell you, in real life, you can actually check this. I'll tell you how. So basically, consider this planet, this Earth, as a huge mass, and these two objects are obviously attracted to this planet. So when you throw them, both of them will reach the ground at the same time. Okay, it does not matter. This, obviously, this marker, I mean, you cannot tell, but this marker is actually heavier than this duster. This will reach at the same time as this will reach the ground. So it really does not matter. The mass of a smaller object really does not affect the acceleration of that object towards the ground. But however, something will depend. See, if the object is above here, the acceleration, the force is less than the object is here. So the distance from the object to the bigger object actually matters. So the acceleration of the planet does not depend on its mass. So for example, if you have a satellite going around the planet, the acceleration of the satellite does not depend on the mass of the satellite. Same way as a planet is revolving around the sun, the acceleration of the planet does not depend on its mass. Okay. So we have 3 conclusions. I hope you guys have written them down. So we will go ahead and we will do some further calculations, okay? So one of the calculations that we will go ahead and we will do is here. We have the position vector r. The position vector r can be written as the magnitude of r into the unit vector, okay? Now, if we differentiate the position vector, we get the velocity vector. The velocity vector is actually given by r. So we will differentiate one part and we will go ahead. We will go ahead and actually we will keep the other part as it is. So when we differentiate this part, it will be dr over dt into u plus u dr into u r. Okay. Actually, let's write u to be du over dt, and then we can write this as r. So now I'll take the cross product between these two vectors right there. The cross product of the position vector and the velocity vector. So the cross product of the position vector and the velocity vector can be given by the cross product can be easily be given by let's take the cross product, so it will be RU into dr over dt into the vector u plus the differentiation of the vector u into the magnitude r. So when we take the cross product, we see that we notice something. So let's do this cross product right here. It will be r dr over dt, cross product of the vector u with its own self, plus r square, and then we have the vector u cross product with its derivative. Okay, so now we have the vector u cross product with its own derivative. So let's see, what do we have here? So once we get this done here, once we get it done here, we have some conclusion. This will actually be equal to 0. Okay, and this will remain as it is. So let's write down here. Okay, so you guys got this expression? Okay, perfect. This is 0 because the unit vector is, when you take a cross product of a unit vector with its own self, any vector having a cross product with its own self will always give the value of 0, because that vector will either make 0 degrees or 180 degrees with its own self. So mostly if it's a vector with its own self, it's always 0 degrees. So you'll always have the cross product of a vector with its own self is always 0. So this part goes away. So our next step would actually be going ahead and focusing on this formula itself. Okay, so let's go ahead and focus on this formula. I will go ahead and I will write down this formula again on the top. So because all my further derivations will be based on this particular formula. So the cross product of the position vector of the planet with its velocity vector of the planet is given by the magnitude of the planet square into the u vector, the unit vector, and the cross product will be du over dt. Okay, so I'll remove this part from here and let's focus. Let's now take the left-hand side only, and let's take the differentiation of the left-hand side. So, the differentiation of the left-hand side. So what do we get? When we take the differentiation of the left-hand side, we will first differentiate one, keep the other as it is, and then go ahead and differentiate the second one, and then keep that as it is. So let's do that differentiation. When we do the differentiation, we have dr over dt into the velocity vector plus dv, the differentiation of dv over dt into the position vector of the planet. So this can be further written down as So you see, the differentiation of the position vector right here will actually give us the velocity vector. So the velocity vector of the cross product of the velocity vector with its own self plus the differentiation of the velocity vector will give us the acceleration vector into the position vector. Okay? So now we have this thing. So now we can further go ahead and compute. As I mentioned several times earlier, the cross product of a vector with its own self is actually 0. So this will be 0. And as I told you, when a vector is parallel to one vector or completely opposite in direction to this vector, as I mentioned, acceleration is completely opposite to the position vector. It was one of the conclusions that we derived from this formula that the cross product of two such vectors will also be 0. So this answer is equal to 0. So now what we will do is we'll focus on this part. So let's remove everything else. Let's write this. Is equal to 0. So this gives us actually a very important conclusion. What is the conclusion? Sorry for that. To get that conclusion, let us integrate on both the sides. When we integrate on both the sides, we are left with, so this vector is actually a very special vector. This is a constant vector. Let's say it is a constant vector. And this particular vector actually is perpendicular to both the position vector and the velocity vector. Okay, so now let's go ahead and let's actually write them down. Let's write these two formulas down. So I have C is actually equal to RU and into the cross product of du over dt. So let's draw the diagram. Let's see what it actually means, because C is both orthogonal or perpendicular to the position vector and the velocity vector. Let's say this is the z-axis. Okay. This is the x-axis. This is the y-axis. Now this is the origin. This is where the sun is. Okay. The planet is revolving like this. Okay. If this is the position vector of the planet, the vector C. So for simplicity, both the position vector and the velocity of the vector lie in the xy plane. So we have proven that the planet's orbit is in one plane. So let's write this assumption right here. The planet's orbit, the planet orbits in one plane. In one plane. Okay? So if the planet is orbiting in the xy plane and the c vector is actually perpendicular to both the position vector and the velocity vector, the c vector would be somehow parallel or maybe even lying in the z-axis. This is how it is. Okay? So now let's move on, guys. And let's see our next step. Our next step is actually to take the cross product of the acceleration vector with the constant vector. our goal is to find the cross product right here. So what is the acceleration vector is given right there. So I will remove these parts. Okay. And it was actually r squared here. It was not the vector r. Sorry for that. And let me just remove this. So we have here our acceleration vector, and the cross product with the c vector will give by, let me write it below, will give you, so the acceleration vector is negative gm over the magnitude of the position vector square u cross product of, okay, this is the acceleration cross product of the acceleration vector with the position vector. First, we can easily simplify, and we can write them as perfect. Okay guys, from here we can go ahead and write this down as is negative gm u, negative gm u into the dot product of du over dt into u minus u into u, u into u, and then obviously into du over dt. Okay, so guys, here we have something very special. If you notice this thing, if you notice that this will actually go into zero. Why it is zero? Because when a vector is having a magnitude of 1, so the unit vector is a unit vector, so it's having a magnitude of 1 or a constant, then that particular vector is actually perpendicular to its derivative. So the cross product of two perpendicular vectors is actually equal to 0. So this will go away. This term will actually go away. Okay? And this term will be remaining. So we will be remaining with the cross product of the acceleration with the constant vector is actually positive, because negative and negative will become positive. Gm u into u, so it will be dot product. So the angle between them is 0, so cos of 0 is 0, and then the magnitude of u is 1, so it will be 1. So into 1, I'll not write the 1, into the differentiation of the unit vector. And remember, this unit vector is actually representing the position vector. So now let's write this formula in the top again. Is equal to Gm Now this can be written in a very particular manner. This right hand side, we can write this down as because Gm is a constant, so if you include that in the derivative, it actually does not make any difference in the results. So let's now focus on the left-hand side of the equation. The left-hand side of the equation can be written as this, because acceleration is actually the differentiation of the velocity vector, is equal to the right hand side. We already have the right hand side over dt. Okay, so now since c is a constant vector, we can obviously include c in the differentiation. So what we will do is we got this formula right here. Got me? And so now this is a very beautiful formula, because we will come to know one more thing about the path of the planet. So let's now write down this formula at the top, and we'll focus on this particular formula. So this particular formula we'll write here, so I can focus on it now. So now we will study this particular part. Let's go. So now, guys, what we will do is we'll integrate this formula. When we integrate on both the sides, we get the cross product of velocity vector of the planet into the constant vector, which is here, is equal to this particular thing right here, plus our constant vector, let's say C1. Now this C1 is very interesting. We need to know two things about the C1. What are the two things? So, first of all, the first thing that we need to know about the C1 is this C1 is in the same plane as the in the same plane as the position vector. Why? Why is this so? We have to figure that out now. Why is this C1 in the same plane as the position vector, which is the unit position vector in this case, which is u? So now from here we can see that this particular vector is actually perpendicular to the constant vector c. So it's perpendicular to this. Z is perpendicular to c, okay? The z-axis. So this vector must lie in this plane. And why is it exactly in the same plane as the vector u? Because if it goes in some other, if it has, for example, if this constant vector had a z component, then automatically it will go in the z plane, the xz or the yz plane. To stay in the xy plane, this vector will be in the same path or in the same plane as the position vector. And to make things simpler, we will assume that this vector is actually parallel to the x-axis of the elliptical path. And this vector is making an angle of theta. Got me? This vector is actually making an angle of theta. So now let's compute c dot c. So c dot c is actually c squared, okay? So let's compute c squared is equal to, remember, the cross product of the position vector with the velocity vector was actually c. So r into v, r cross product v, and then we have c here. Let's take the c right there. Okay, this can be written as this c square can be written as the cross product of the velocity vector with the constant vector into the position vector. Okay, so now we'll focus on this formula. We are actually approaching the last stages of our derivation of Kepler's law of planetary motion. So now let's go ahead and let's write this down on the top. C square is equal to the cross product of the velocity vector with the constant vector into the vector r. Okay, so now let's go ahead and let's do this. So we have this value right here. So now we'll compute this value and we'll write down a different expression. We'll substitute this vector because we have this vector in terms of a different constant vector, so we'll compute that. So we can write this as GMU plus B, okay, dot R. There we go. So when we have this particular formula, we'll now have to go ahead and furthermore expand it. So before expanding this, we actually can write the position vector C is equal to GM, keep everything as it is, but the position vector here, so the constant vector C is equal to GM into the position vector, unit position vector U, dot product into the constant B. Sorry, this is not the constant. I'm writing a different constant, C1, okay, into the position vector R. So the position vector R can be written as the magnitude of the R into the unit vector. So now let's go ahead and let's write this down. Okay. We'll take, you see this R is a constant, we can take it outside. We can take it outside and then plus R, and we will have so it's this one. So we will have plus here, plus R C1 into R C1 into no, we have already plus C1, and then we are left with C1 into the position vector RU. Okay, so now let's go ahead and let's compute this. So sorry for the inconsistency there. So we'll have the constant vector. This is not the constant vector, guys. I'm very sorry. This will be the constant square. So this, the square of this magnitude is equal to R GM into U dot U. So the two vectors, if they're same, that dot product will give you back 1. We have seen this from different places. Into GM plus R, okay, and then what we will have is this vector right here. So this vector right here is actually, what is it making? It's making a cos theta. So we will compute this dot product right here. We will compute this dot product. When you compute this particular dot product, you actually get here. You can compute the dot product between the unit vector and then the vector C1 cos theta. So C square will go to, this will give you 1, so it will be R GM plus C1. Let's write that this is C1 because C1 is the magnitude of this vector, C1, and then cos theta. So now we can make R the subject of the formula here. R can be written as R. So what we have is here, we have here R, and then what we will have is here R can be written as, if we make R the subject of the formula, this is again C square. C square is equal to R GM plus R C1 cos theta, and then R, if you take R common, the R will not be here, so R is equal to C square over GM plus C1 cos theta. Okay, now we will focus on this equation. So how did we get the equation? So this will always, of course, I am missing an R here, sorry for that. If you guys follow the arithmetic properly, you'll see that R is missing here. And then from there, this cross product, this will go to 1 because the magnitude of the unit vector is already 1. Sorry for saying the word cross product. I'm saying a lot of different things today. And then R into C1, this is the magnitude of this vector, into cos of the angle between them. We have it here. We take the R outside, that is the radius of the path, and then we will notice that C square is equal to R common into GM plus C1 cos theta. And then what we have is here, we have this particular formula, and we'll focus on this formula right now. When we focus on this formula, let me write down this formula on the top. So, let's say I take GM common outside on the denominator. So I will be left with GM 1 plus C1 over GM cos theta. Okay. Now this GM can go on the top. C square over GM. Okay. Now what I need is actually, to be honest, I will need whatever is the coefficient of cos theta here. Sorry, let me just remove this now. Whatever is the coefficient of the cos theta, I would need it in the numerator as well. Okay, so I will get C1, and then I will multiply that with C square over C1 to keep the equation constant, and the denominator will have 1 plus C1 over GM cos theta is equal to R. Let me just write down the formula for R right here in big, and then I can tell you how we have proved the first law. So R is equal to C1 over GM. Actually, let's write C1 over GM into C square over C1, and then 1 plus C1 over GM cos theta. Guys, this is actually an equation, a polar equation for a conic section with eccentricity E, which is equal to C1 over GM. And another thing I want to point out to you guys, so a conic section can have three different kinds of curves: an ellipse, a hyperbola, and a parabola. But the problem is, we know that the planets don't revolve and then escape. That would be very funny and obviously dangerous. the planets stay in a closed loop. So the only closed loop possible is actually a elliptical path. So this is the derivation of Kepler's first law of planetary motion, which says that all the planets stay in an elliptical path around its focus, which is the sun.